Okay, in this tube we'll be dealing more with hardware and setting up pins and designing and accessing hardware with microcontrollers. So this first few we're setting up pin configurations. So we're going to have inputs on P1.2, P1.5, P1.6, and we'll assume the rest are going to be outputs because they haven't been specified. So we say move.b and we say 7, 6, 5, 4, 3, 2, 1, 0. So if there are 1, they're going to be an output. If there are 0, they're going to be an input. And P1 DIR. Next, MSP430 has inputs on P1.1, P1.2, and they should use internal pull-ups. So just as before, we say move.b, and we've got 7, 6, 5, 4, 3, 2, 1, 0. P1 DIR. And then we need to do the resistor enable, the pull-up resistor enable. So move.b 7, 6, 5, 4, 3, 2, 1, 0. P1 DIR. Now finally we also need to decide whether these are going to be pull up or pull down resistors. So we say move.b and we want them pull up resistors, so 7, 6, 5, 4, 3, 2, 1, 0, and we write to the P1 out register. Now when we're dealing with inputs, the P1 out register will tell us whether we're using pull up or pull down resistors. So if you put a 0 in there, it's pull down. If you put a 1 in there, it's pull up. And MSP430 has inputs on those pins and uses the special function of P1.2. So move.b 7, 6, 5, 4, 3, 2, 1, 0. P1 DIR, and then we need to enable special function on that bottom, the P1.2. Move.b 7, 6, 5, 4, 3, 2, 1, 0. P1 SEL. Okay, in the second question we're actually going to be designing a circuit with a microcontroller, so this is more of a hardware question. So we start with an MSP430 microcontroller, so we'll have a box in the middle. And operates from a 3-volt supply with a decoupling capacitor. So we'll have a ground connection. We'll have a decoupling capacitor. So our decoupling capacitor at the sort of frequencies we operate at should be 100 nanofarads. And we have our 3-volt supply. The decoupling capacitor will just ensure it takes some of the ripple out of our supply and ensures our microcontroller has a fairly nice even voltage to deal with. It'll effectively decouple it from the rest of the circuit. We then have some switches, and these use our external pull-up resistors. So why don't we put them over this way here. So one switch with an external pull-up resistor, a second one with an external pull-up resistor, and a third one. So we have our 3 switches. So we'll just label these R1, R2, R3. And then we need 2 LEDs. So LEDs need a current limiting resistor. We draw our LED, make sure we have the arrow there that indicates it actually emits light, otherwise it's just a diode. Common mistake people make. And we'll call that R4 and R5. So LEDs are connected to P1.0, P1.0 and P1.5. Switches are connected to P1.1, P1.3 and P1.4. Okay, so our R1, R2 and R3 resistors will all be the same, and we'll have them as 10k. So they'll pull up the voltage when the switch isn't being pressed, so the pin doesn't float, and they need to be large enough so that when we press the switch we don't effectively provide a short circuit to ground. So if we've got 3 volts there, 10k, we've only got a very tiny amount of current flowing through here. R4 and R5 we need to calculate though. So in this case we've got R4 is equal to R5, which is equal to, we've got 3 volts here, so 3 volts. I didn't specify a V output low max, so we don't need to include that in the calculation. We'll assume it's 0 in this case. Minus 1.9 volts, which was the forward voltage across our LEDs, divided by, we wanted 10 milliamps of current, so 10 milliamps. So when we calculate that out, 10 milliamps is 0.01 amps. It gives us 110 ohms. Closest value to this is closest value that we commonly have in our sort of 5% range is our 120 ohm resistor. So we'd use a 120 ohm in that case, so it would be slightly dimmer. We also need to write a line of code to set up the port directions. So we say move dot B, and we've got pin 7 is not connected, so it's an output. Pin 6 is not connected, so it's an output. Pin 5 is an output, it's the LED. Pin 4 is an input. Pin 3 is another input. Pin 2 not connected, so it's an output. Pin 1 is our other switch. Pin 0 is our other LED to P1 DIR. A question like that's worth probably 7 or 8 marks on the exam. Okay, these questions here, fairly basic questions that get us to calculate our current limiting resistors. It's really important that we're able to calculate a current limiting resistor for interfacing an LED with a microcontroller. This subject isn't just about software, it's about hardware as well, and interfacing hardware in circuits. So we know our equation looks like VCC minus V output low max minus the LED forward voltage divided by the forward current of the LED. So forward voltage is this one here, the forward current is that one there, 15 milliamps. So 5 minus 0.5 minus 1.8 divided by 0.015, 15 milliamps, should give us 180 ohms. In this case we've got R equals 3.3 minus 0.3 minus 2.1. We've got a pretty low voltage happening there, and we've got 10 milliamps. So that will give us 90 ohms. The closest common value we've got is 100 ohms, so we'd use 100 ohms in that case. Okay, now we're doing some debouncing. We want to write code to debounce the switch on P1.0 or P1.2. We've got 1,000 delay cycles that we want to delay it for. So probably easiest if we first write our flow diagram to show what's going to happen, and then we write some code to make that work. So flow diagram first. So we start up here. We set a counter to 1,000. We'll just call it I equals 1,000. So this is going to allow us to have our 1,000 delay cycles. We say if switch is pressed, so here we say false, our switch isn't pressed. We'll go back to here and reset our counter to 1,000 again. Otherwise, if it is pressed, we decrement our counter by 1. I equals I minus 1. We can then check if our counter is 0. If I equals 0, if it's not equal to 0, we need to keep our debouncing going. So we go back up here. If it is equal to 0, we're debounced. Okay, let's write some code to reflect this. So here we say we want to move a value of 1,000, and for argument's sake let's use R15 as our register. Now we need to jump back to this point here, so we'll put a label there. In this case we'll call it main. We need to also jump to this point here, so let's call that one, it's just before we're testing the switch, so let's call it test switch. Okay, so we've got our labels in place. Now we need to see if this pin P1.2 is high or low, and you remember from the inputs lecture we use the bit command to do this. So bit.b, because we're using a byte here, not a word. We're interested in pin 1.2, so 765432210 P1 in. So we're checking whether this pin is high or low. We want to say jump not 0 to main. So we're essentially saying jump if that pin is at a high voltage because it's not 0. Now remember, when we press our switches they go to a low voltage, so it's saying jump if it's not pressed to main. Otherwise we want to dec R5, and we can then say jump not 0 to test switch, and after that we can say debounce complete. Okay, our next one is very similar to what we've done in the lectures. We're essentially wanting to flash an LED on and off and have some delay times in there. So we'll first do our flow diagram because that's what we've asked for. So if we say start, we then jump through and say LED on, we delay, LED off, and delay. Now we can actually optimize this a bit further, and obviously we need to loop back around a bit. We can optimize it a bit further, and I'll show you the code for both of them. So our other way of doing it would be to go like this. So we say start, we say toggle LED, and you remember we use the XOR for toggling. We delay, and we're done. Okay, let's write some code very quickly to implement each of these. So if we want to turn an LED on, we need to set the pin to 0. It's on P1.2, so we want to clear it. So we say, or here we'll have our main. We'll say bit clear .b 76543210 P1 out. Kind of running out of room there a little bit. Okay, then we want to call our delay. So call hash delay. We want to set the pin high to turn it off. So bit set .b 76543210 P1 out, and we want to call delay again. And finally we want to jump to main. Okay, now we'll go with the toggling method. So this is this method from up there. We need a label to jump to, so let's just call it main for want of a better one. Now we use XOR to toggle a bit, so XOR.b 76543210 P1 out, and then we have to call our delay. And then we end it, of course, in a jump main. Okay, final thing that we need to do is we need to actually create that delay routine, which we didn't create before. So we'll quickly create a subroutine to do that. So our delay subroutine, this is where we start it. We put a value in there that we want to delay by. So I equals 10,000. We say I equals I minus 1. We say is I equal to 0. If it's no, it's obviously greater than 0, we keep on counting down, and if it's yes, we end. It's over. Okay, so we can pretty quickly write some code to do this. So we've called previously our delay subroutine delay, DLY, so that's the label that we're going to be jumping to. So for this one we'll use register 14, so we'll move the value 10,000 to register 14. We then need a spot to jump back to, so we'll call it loop delay, for want of a better word. We need to decrement R14, and we need to do a jump not 0, so jump while it hasn't reached 0 yet to loop delay. Then we have a thing that all good subroutines end with. We have a return statement, so RET, and we go back to the start again. So there we have it, two different ways of implementing the LED flasher, either setting it high and low explicitly and delaying in between, or toggling it using the XOR command, XOR logic, and then delaying, and then we have the loop delay as well.